Hi everyone. In this new video, we're going to introduce some new concepts, especially the rational method. So let's get started. In problem 3.1 says, imagine a flat parking lot that doesn't absorb any water. It rains very hard on this parking lot for 1 hour with a peak rain rate of 2.4 inches per hour lasting for 10 minutes. All the rainwater immediately runs off the parking lot without collecting in puddles. Given that the parking lot is 2.5 acres in size and the total rainfall is 1 inch, we need to figure out two things. First, how much total water fell on the parking lot, or total precipitation in cubic feet. Same thing. Second, what was the fastest rate at which water flowed off the parking lot? Or in other words, we need to find the maximum runoff in cubic feet per second. The book mentions a impervious watershed, and impervious means that the water doesn't infiltrate or percolate into the groundwater. So a parking lot fits these characteristics. That's why I use this for this problem. Now let's start solving one by one. Um, so part one is asking us for the total precipitation. Uh, I have a formula here. Uh, Total precipitation will be the volume equals the precipitation in inches times the area. um, the volume of precipitation. So what I'm trying to say here, if you remember on the very first video when I talked about precipitation, it could be represented as either inches or uh, cubic feet. And the reason why, or also it could be feet or cubic feet, right? And the reason why there are two different units for that is because we'll need to multiply the depth in feet times the area to get cubic feet. And same thing with inches. We need to convert this into feet first and then multiply it times the area to get cubic feet. Precipitation as a volume in cubic feet. So in our case, we are given, says the parking lot is 2.5 acres in size and the total rainfall is 1 inch. So total rainfall means precipitation. So we want to find the total precipitation. We need to multiply the 1 inch times the area. It's 2.5 acres. Now, and we want it in cubic feet, so we need to do some conversions. So we need to multiply this by 1 foot over 12 inches. So we cancel inches, and we need to multiply in 1 acre. There are 43,560 square feet. That way we cancel acres, and we will have precipitation equals 2.5 times 43,560 square feet all over 12. Um, Sorry, and then it should be this feet times square feet should be cubic feet. So this is going to be, if we use Excel, uh, equals 2.5 times 43,560 divided by 12. We get 9,075 cubic feet. Let me check that with the answer. That looks familiar, but that's correct. So that's the answer for part one. Now for part two, we were asked what was the fastest rate at which water flowed off the parking lot or max runoff. Here's where we're gonna use our rational method equation, which is outflow rate equals CIA, and there is a conversion factor here that I'm going to explain how we get this value from. So from this equation, we need to know that C represents the runoff coefficient, I is the intensity, and A is the contribution area, or just the area of our study or our case. So we have that for C, the runoff coefficient, we have a impervious watershed, or in our case, a parking lot. So this is going to be, let me write down, Q equals CIA. So in our case, C is gonna be 1 because 100% of the water that falls on our area is going to run off. And then we are given that the maximum intensity is 2.4 inches per hour. Um, we are also given that this intensity lasts 10 minutes, but we actually don't need that information. We don't need how long uh, the maximum intensity um, lasted. And now the area is 2.5 acres. So plugging these values in Q to solve for Q, in our case Q max, will be 1 times 2.4 inches per hour times 2.5 acres. Now, this is going to be Q max equals 6 inches per hour times an acre. And we are being asked to represent this in cubic feet per second. Now, the reason why there is a 1.08 as part of the equation is because if we try to convert this to cubic feet per second, let's say there are 43,560 square feet in 1 acre, and we multiply this by 1 foot over 12 inches, and then multiply this by 36, it will be 1 hour 3600 seconds. So we can cancel hours, we cancel inches, and we're only left with the cubic square feet times feet per second. We're gonna have 6 times 43,560 over 12 times 3600, and this is gonna be cubic feet per second, which what we are being asked. And this um, this number right here turns out to be 1.008. So it's actually very close to 1, and that's where we find this relationship that if we have, initially we have 6 inches per hour, which is inches per hour is intensity, times the acres, which is the area, we can assume that this is already 1, and we can make an assumption that 6 inches per hour times acres, it's about the same as 6 cubic feet per second. I hope this makes sense. And this is the reason why we use 1.008 as a factor to convert it inches per hour times acres into cubic feet per second. If we solve for this, I believe it's about 6.05, I think, cubic feet per second, which it's like pretty much negligible. 0.05 cubic feet per second is pretty much negligible. So it will be correct as well to just use 6 cubic feet per second. Um, so that's this part. Let's go to the next problem. 3.2, develop a hydrograph graphical presentation for the following rainfall data. Plot the intensity of inches per hour for 30-minute intervals. So we are introducing what a hydrograph is now. We're also gonna be getting familiar with a hydrograph. And the main difference between a hyetograph and a hydrograph is that a hydrograph is flow cubic feet per second over time. So you would usually, for a hydrograph, you have your y-axis, x-axis. In your x-axis, you have time for a hydrograph, and in your y-axis, you have cubic feet per second of a stream flow, outflow, but these are the units. And for a hydrograph, you also have your y-axis, x-axis, and then you have time, and here is inches per hour. So your y-axis in a hydrograph is intensity, and in a hydrograph is a stream flow. So those are the main differences. In this problem, we're asked to do a hyetograph. So we have the time intervals, we have time, we need to solve for the y-axis, which is the intensity. So I'm gonna show you how to do that based on cumulative rain. What cumulative rain means is that the first 30 minutes we got 0.04 inches of rain, and in 60 minutes we got in 60 minutes we've got 0.38, and it's like pretty much adding up, it's accumulating all the rainfall throughout time. To find the intensity, we need to convert this into just values per each 30 minutes, for each 30-minute interval. So first, let's just calculate the rain in inches per interval. That would be, in our case, the first 30 minutes was 0.04. In the second 30 minutes, it will be 0.38 minus the previous one. That means that in the second 30 minutes, 0.34 inches of rain precipitated. And this, we keep doing the same, this minus the previous. And if I drag it, hopefully that, that should work. So this is our rain difference per each interval of 30 minutes. Now, for intensity, we need inches per hour. So in our case, intensity of inches per hour, we got the inches already, so we just need to divide it by time. And we have this value divided by its time, but in our case, it's 30 minutes. So we need to convert it to 2 hours, right? We don't want inches per minute, we want inches per hour. So we need to multiply this times that are 60 minutes in 1 hour. So it will be 60 and minutes. Okay, so we have to absolute this value, and hopefully now it's gonna work. If it wants to, probably. There we go. Now we're getting these values, and let me, if it that what I didn't make sense, I'm just converting from inches per minute to inches per hour. So what we did, we had 0.04 inches, and we wanted to divide it, in our case, in intensity of the first 30 minutes, it will be divided by 30 minutes. But we want to convert this into inches per hour. So there are 60 minutes. We multiply that by 60 minutes in 1 hour. So this is all I did, and that's how I got 0.08 inches per hour, because the minutes cancel. That's it. Now we just need to plot intensity versus time. So let's see. I like better to use Excel, but let's see how we do it on Google Sheets. So you use insert chart, then you will want to use a column chart. Let's select our data range. So we can select all of the data, and then we just select specifically what we want to plot. So now that we have all the data selected, we only want the intensity. So we're gonna remove rain, cumulative, and time. We don't want it in the y-axis, we want it in the x-axis. So we just leave in the y-axis in series, we just leave intensity. And now in the x-axis, we select time. And this is a hydrograph. It's the intensity versus the time. And we'll just need to uh, add, add the titles, horizontal axis title, and that will be time. In our case, it's in minutes. And we go to vertical, intensity, inches per hour. Okay, so this will be the hyetograph of according to this data that we were given. And usually in a hyetograph is represented without these gaps here, so you can do a little more work and eliminate the gaps and make all the columns be right next to each other. Now let's move to problem 3.3. In this problem, we are introducing IDF curves, or intensity duration frequency curves. And this problem is mainly to help us understand how to use this graph. So we're given that in 3.3, what is the average rainfall intensity for a 1 hour and 6 hour rain event? So we have two rain events. It says with a return period of 100 years for the Orange County, Florida area. Use the intensity duration frequency IDF curves of Appendix C. So that's the place where I got this IDF from. And let's make this bigger. So we are given two storms. Says what's the average rainfall for a 1 hour and 6 hour rain event. So in an IDF curve, in the x-axis you have the duration of the storm, and in the y-axis you have the intensity of in the units of inches per hour of precipitation. So these curves, each one of them represents a different return period. We are asked to determine was it the 1 hour? Yeah, 1 hour and 6 hours for a 100-year return period. So if you follow this one and you're careful, will be the second line from the top in this IDF curve. So for 1 hour, it will be about 60 minutes. You just follow that line until it crosses the return period line that you're interested in. In our case, will be the second one from the top, and then you go to the left, which it will take us to about 5. If you look more closely, you will notice that it's a little below 5. So I would say it's about 4.9 or 4.85. So that will be the intensity of a 1 hour storm in a 100-year return period. So the answer for that part will be about 4.85 inches per hour. Let's do that. For 1 hour, it will be 4.85 inches per hour. And for a 6 hour, we follow a very similar process, except that we now go to the 6 hour line in the time axis, go up, and then move all the way to the left. And it will take us, that is about 1.3 inches per hour. And that's how you use an IDF curve. It's pretty simple. Now, this is it for this problem. Problem 3.4 will ask us to use actually this data. So let's copy this and let's plug it somewhere in here. So problem 3.4 says, what is the total rainfall volume of the storms of problem 3? So we have the intensities of each storm now. Now we need to find the total rainfall or total precipitation, which the formula is this one here. Precipitation equals the intensity that we solved for in the IDF times the time difference of, or just the time of the storm. It will be just the time of the storm in our case. So for part A, for the first storm of the 1 hour storm, our precipitation will be equal to our intensity, which is 4.85 times the time, which in our case is 1 because it's 1 hour. So it will be about exactly the same value, 4.85 inches of precipitation. We have inches per hour times hour, that will give us inches. Now for the second storm, oh, we have the intensity, which is 1.3 1.3 times the time, and our storm is 6 hours, so it will be times 6, and that will give us 7.8, also inches because it's inches per hour times hour. So these are the solutions for this problem. Precipitation of a 1 hour storm according to the IDF curve would be 4.85 inches, and for a 6 hour storm would be 7.8 inches. In the last problem of this video, we're gonna solve for problem 3.5, which says, if 55 millimeters of rain is recorded for a 6 hour storm by one rain gauge for a watershed area of 10 square kilometers, but the runoff from the watershed indicates only 45 millimeters of rain has fallen on the entire area, what is the area reduction factor? And then how does this compare to the results reported in the UK? Table 3.7, we have it here. What this is saying is that in this storm that lasted 6 hours, there was recorded 55 millimeters of rain over all this area. We don't know the area, we don't need to know. We are given the precipitation in only the depth of the volume, 55 millimeters. However, once all this amount of water gets to the ground and runs off, there is a gauge on this stream that indicates only 45 millimeters of of the precipitation of the rain, which means there was some water that was lost in the air between, I would say, between the clouds and the ground. So that is called area reduction factor. And all we need to do for this problem is use the, the runoff volume divided by the precipitation. Something very important is this runoff volume. It's a volume, it's not a volume rate, it's not cubic feet per second. So if in another problem you are given a cubic feet per second, you have to multiply that value times the 6 hours of the storm, so you can get only the precipitation, or sorry, so you can get only the runoff as a volume. So in this problem, it's very simple. We just need to plug the 45 millimeters divided by 55, that is the precipitation, and that will be our percentage, well, our value of area reduction, which means that out of the 100% of water that precipitated, only 81%, about 82% of it made it to the ground. And we need to compare it with table 3.7 now. And in table 3.7, we have for a 6 hour storm duration. We actually were given the kilometers in the area, sorry. But we don't need to convert it to find the area reduction factor. We don't need to convert into cubic feet. No, in our case would be into meters, cubic meters. And now we just need to convert it. It will be, the area is 10 kilometers square kilometers, so it would be, according to this table, the reduction factor, area reduction factor, will be 0.96, and comparing both, we can tell that our value in our case, it's much slower than the ones reported for the UK. So yeah, a couple few new concepts and graphs that we need to get familiar with. I hope this video was helpful, and good luck solving out these problems on your own.